Long ago, the sky and stars have been the place where humans strained their eyes in anticipation and entrusted their fate to the gods. Since ancient times, from the moment when humans still used fire to ward off wild beasts and used sticks for hunting and gathering, we have gazed at distant nebulae and wondered where they came from. No one knew that the intelligent Homo sapien, after more than 40,000 years of existence, had reached a level where they could explore the roots of the universe. Humanity has taken tentative steps from its early days with the astronomical lens in the hands of Galileo to the shining presence of James Webb in space. 10 years ago, humanity recognized the greatest discoveries as being Hubble and the Big Bang Theory. 10 years later, that knowledge is gradually crumbling under new evidence from James Webb. As an intelligent audience, I wonder what you would choose, to stay with the past and believe in long-standing hypotheses or join me in an adventure to a new horizon where all your knowledge will be challenged and transformed. Right now, James Webb will represent all of humanity, writing an epic ode for the cosmic journey to the distant universe and welcoming you to ICE 200M, where thrilling adventures begin with boundless knowledge. Why does humanity need an astronomical instrument like James Webb? The truth is that astronomical telescopes also have limited visibility like the human eye. Their structures are incredibly complex but all operate on a common principle. You can imagine this principle simply as follows: to look back at the early stages of the universe and witness the first twinkling stars, we first have to polish a mirror the size of a house. Its surface must be smooth to the extent that if the mirror were the size of a continent, it would have no hills or valleys higher than the base of the foot. Only a very large and smooth mirror can collect and focus the faint light coming from the farthest galaxies in the sky, light that has left its source long ago and thus reveals galaxies as they appeared in the ancient past when the universe was still young. The faintest, farthest galaxies that we see are still in the process of formation, as mysterious forces conspire in the darkness and the first stars begin to shine. But to read the first chapter in the history of the universe, to understand the nature of the first stars, perhaps gigantic, to learn about the invisible matter whose gravitational forces have caused their existence, and to explore the roles of magnetism and turbulence as well as how massive black holes develop and move toward the centers of galaxies, a special mirror alone is not enough. The reason no one has seen the epic of galaxy formation is that the light from ancient stars, after traveling to us through the expanding structure of space over billions of years, has been stretched. The ultraviolet and visible light emitted from the farthest stars in the sky extends to wavelengths about 20 times longer on its journey to us, becoming infrared radiation. But infrared light is a type of atomic oscillation light that we call heat, the same type of heat radiated from our bodies, the atmosphere, and the ground beneath our feet. Alas, these local heat sources have extinguished the pitiful flames of the primordial stars. To observe those stars, a telescope with its large perfect mirror must be very cold. It has to be launched into space. Speaking of missions, James Webb is the perfect heir to its predecessors. With the Hubble Space Telescope, we have learned that stars, galaxies, and supermassive black holes existed much earlier in the history of the universe than anticipated, and since then they have undergone fundamental changes. We know that dark matter and dark energy make up the universe. With telescopes like Kepler and others, we have seen that all kinds of planets adorn galaxies like ornaments on a Christmas tree, including billions of potentially habitable worlds solely within our Milky Way. With James Webb, humanity expects an entirely new exploration of the history of the universe. Discoveries from previous generations of telescopes have raised questions that the James Webb Space Telescope can potentially answer. Astronomers also hope that, like other telescopes, seeing it in action will pose new questions. Ma says every time we build a new observing device, we get a surprise. Grant Tremble, an astrophysicist at Harvard University who serves on the time allocation committee for the telescope, notes this will be our dare to be great moment. It will do amazing things. We will be on the front page of the New York Times talking about witnessing the birth of stars on the edge of time. How this is one of the earliest galaxies, this is the story of other Earths. As a result, James Webb is poised to challenge even the longest-standing theories in astronomy. JWST discovers massive black holes across the early universe. Years before it was certain that the James Webb Space Telescope would successfully launch, Christina Isers began planning a conference for astronomers specializing in the early universe. She knew that at best, when JWST began its observations, she and her colleagues would have a lot to talk about. Like a time machine, the telescope could peer farther and deeper into the past than any previous instrument. Fortunately for Isis and the rest of the astronomical community, her plan was not in vain. JWST launched and deployed without any hiccup, then began scrutinizing the early universe meticulously from its position millions of miles away in space. In mid-June, around 150 astronomers gathered at the Massachusetts Institute of Technology to convene the first Light JOST conference organized by Isis. Less than a year had passed since JWST began sending images back to Earth, and just as Isis had predicted, the telescope had reshaped astronomers' understanding of the first billion years of the universe. A set of enigmatic objects stood out in numerous presentations. Some astronomers referred to them as hidden little monsters, for others, they were tiny red dots. Regardless of their names, the data was clear, as JWST peered intensely at young galaxies appearing as red dots in the darkness, it observed a surprisingly large number of swirling storms moving at their centers. Isis, an astronomer at MIT, said it seems there were many sources that we didn't know about that we couldn't predict we would find. In recent months, a series of observations of fuzzy traces in the universe has both fascinated and puzzled astronomers. Zhi Fan, a researcher at the University of Arizona who has dedicated his career to searching for objects in the early universe, stated people are talking about these tiny red dots. The simplest explanation for galaxies with swirling storms is that massive black holes weighing millions of suns are causing the gas clouds to go berserk. The discovery is both expected and perplexing. It is expected because JWST was partially built to search for ancient objects. They are the ancestors of the billions of solar mass black holes that seem to appear early in the cosmic record. By studying these precursor black holes, such as the 3 record-breaking black holes discovered this year, scientists hope to learn where the first massive black holes come from and perhaps determine which of the two competing theories more accurately describes their formation. Do they grow extremely rapidly, or were they simply born large? However, observations also bring confusion because few astronomers expected JWST to find so many young and hungry black holes. Surveys are uncovering dozens of black holes. In trying to unravel mysteries, astronomers have discovered a series of hefty black holes that could rewrite established theories about stars, galaxies, and more. Marta Vollen, an astrophysicist specializing in black holes at the Paris Institute of Astrophysics, says as a theorist, I have to build a universe. Vollen and her colleagues are now grappling with the influx of massive black holes in the early universe. If they are real, they will completely change the picture. A cosmic time machine, JWST observations are shaking up astronomy in part because the telescope can detect light reaching Earth from deeper space than any machine before it. Grant Tremble, an astrophysicist at the Harvard-Smithsonian Center for Astrophysics, says we've been building this incredibly powerful telescope for over 20 years. Its original purpose is to look deep into cosmic time. One of the mission's goals is to capture galaxies in the process of forming in the first billion years of the universe, out of approximately 13.8 billion years of its history. Early observations from the telescope last summer hinted at a universe filled with astonishingly evolved galaxies. But the information astronomers can gather from such images is limited. To truly understand the early universe, astronomers not only need images, they crave the spectra of those galaxies, data obtained when the telescope separates light into specific colors. The spectra of galaxies that JWST just began sending back in earnest at the end of last year are invaluable for 2 reasons. Firstly, they allow astronomers to determine the age of the galaxy. The infrared light collected by JWST appears red, or redshifted, meaning that as it travels through the universe, its wavelength is stretched due to the expansion of space. The degree of this redshift allows astronomers to determine the distance of a galaxy and consequently pinpoint the time it initially emitted light. Nearby galaxies have redshifts nearly 0. JWST can easily generate objects exceeding a redshift of 5, corresponding to about 1 billion years after the Big Bang. Objects with higher redshifts will be older and much farther away. Secondly, spectra help astronomers understand what is happening within a galaxy. Each color marks the interaction between photons and specific atoms or molecules. One color may originate from a hydrogen atom flickering as it settles after a collision, another signifies oxygen atoms being pushed, and yet another represents nitrogen. The spectrum is a color pattern that reveals the composition of a galaxy and the factors at play, providing unprecedented context for galaxies at distances never seen before. Ayush Saksa, an astronomer at the University of Oxford, says, "We have taken a big leap. In fact, we are talking about the chemical composition of 9 redshifted galaxies, which is entirely remarkable." Galaxy spectra also serve as the perfect tool to identify the main disruptor, massive black holes lurking at the centers of galaxies. The black holes themselves are dark, but when they consume gas and dust, they tear apart atoms, emitting various colors. Long before JWST was launched, astronomers hoped that the telescope would help them discover these patterns and find enough of the largest and most actively feeding black holes in the early universe to unravel the mysteries of their formation. James Webb unveils a mystery from 20 years ago. The mystery began over 2 decades ago when a team led by Fan discovered one of the farthest galaxies ever observed, a brilliant quasar or a galaxy intricately linked with a supermassive black hole in vigorous operation, weighing possibly billions of suns. It had a redshift of 5, corresponding to about 1.1 billion years after the Big Bang. With subsequent surveys of the distant sky, Fan and his colleagues consistently shattered their own records, pushing the redshift boundary of the Standard Candle to 6 in 2001, and finally to 7.6 in 2021, merely 0.7 billion years after the Big Bang. The challenge lies in the seemingly implausible creation of such massive black holes in the history of the universe. Like any object, black holes need time to develop and form, akin to a toddler suddenly growing to a height of 6 feet. Fan's supermassive black holes are too large for their age. The universe isn't sufficiently large for them to accumulate billions of suns in weight. To explain these excessively massive youngsters, physicists are compelled to consider 2 uncomfortable options. The first scenario involves Fan's galaxies initially containing numerous standard black holes with masses approximately equal to stars, often left behind by supermassive explosions. Subsequently, they grow by merging and consuming gas and dust in their vicinity. Typically, if a black hole attacks vigorously enough, a radiation stream will push its debris far away. This prevents ravenous consumption and sets a speed limit for the black hole's growth, known as the Eddington limit. But it's a soft ceiling. A continuous dust stream can override the radiation emission. However, it's challenging to imagine sustaining such super Eddington growth long enough to account for Fan's behemoths. They would have to grow at an unimaginable rate. Alternatively, perhaps black holes could be born with sizes so large it's almost unbelievable. Gas clouds in the early universe may have collapsed directly into black holes weighing thousands of suns, creating objects known as heavy seeds. This scenario is also hard to accept because such massive, compact gas clouds would collapse into stars before forming black holes. One of JWST's priorities is to assess these scenarios by looking into the past and capturing the fainter ancestors of Fan's galaxies. These predecessors are not entirely pristine, they are galaxies with slightly smaller black holes on the path to becoming pristine. With JWST, scientists have the best chance to discover black holes that haven't started growing yet, objects young and small enough for researchers to determine their infant weights. That's why a group of astronomers from the Cosmic Evolution Early Release Science Survey, led by Dale Cucci of Colby College, started working overtime when they first noticed signs of such young black holes appearing in the days after Christmas. Jan Kalape, an astronomer at the Rochester Institute of Technology, wrote, "It's impressive how many of them exist. These black holes are too large and growing too fast." In the Sears spectrum, some galaxies immediately reveal and likely harbor tiny black holes. These small monsters, unlike their more discrete counterparts, emit light not in just a distinct shadow for hydrogen. Instead, the hydrogen lines blur or spread into multiple colors, indicating that some light waves are compressed as the gas clouds accelerate towards the JWST, similar to an ambulance approaching, emitting an increasingly high-pitched siren as the sound waves are compressed, while other lines stretch as the clouds move away. Kevy and his colleagues know that a black hole is almost the only object capable of ejecting hydrogen in such a way. Kevy said the only way to see the Y component of the gas swirling around the black hole is if you look straight into the center of the galaxy and straight into the black hole. At the end of January, the Sears team attempted to draft a description of 2 of the hidden small monsters, as they call them. After that, the team began systematically researching a broader range, including hundreds of galaxies. Their program collected to see how many black holes are out there, but they were beaten to it by another team led by Weishi Hurricane at the University of Tokyo. Just a few weeks later, Hurricane's team searched for the farthest 185 Sears galaxies and found 10 galaxies with white hydrogen lines likely due to central black holes with masses of millions of suns at redshifts from 4 to 7. Then in June, an analysis of 2 other surveys led by Jor Matey at the Swiss Federal Institute of Technology Zurich identified an additional 20 small red dots with white hydrogen lines, black holes rotating around a redshift of 5. An analysis published in early August announced dozens more dots, some of which may even be in the process of growing through mergers. Vollen said, "I've been waiting for these for a very long time, it's unbelievable." But very few astronomers predicted the large number of galaxies with active massive black holes. The baby galaxies in the first observations of JWST are more abundant than scientists predicted, based on a population survey of mature galaxies richer by 10 to 100 times. Isers, who contributed to the small red dot paper, said it's surprising for an astronomer when we're off by a large factor or even more than that. Stephanie Juneau, an astronomer at the NOIR lab of the National Science Foundation and a co-author of the paper on small monsters, said there's always a sense that at high redshifts, these galaxies are just the tip of the iceberg. We can see that underneath this Sears population is even larger than the regular iceberg. These two go to almost 11. But to get a glimpse of these monsters in their infancy, astronomers knew they had to go beyond redshift 5 and peer deeper into the first billion years of the universe. Recently, some teams have discovered black holes feeding at distances that have never been seen before. In March, an analysis by Sears, led by Rebecca Larson, an astrophysicist at the University of Texas, Austin, found a broad hydrogen line in a galaxy with a redshift of 8.7, 0.57 billion years after the Big Bang, setting a new record for the farthest discovered actively feeding black hole line. But Larson's record was broken just a few months later when astronomers collaborated with JADE's JWST Advanced Deep Extragalactic Survey and obtained the spectrum of GN-Z11 at a redshift of 10.6. GN-Z11 lies at the faintest edge within the reach of the Hubble Space Telescope's vision. Scientists eagerly study it with sharper eyes. By February, JWST had spent over 10 hours observing GN-Z11, and researchers could immediately tell that this galaxy is peculiar. Jan Schultz, a JADES member at the University of Cambridge, said its abundant nitrogen completely exceeds the limit. Seeing so much nitrogen in a young galaxy is like encountering a 6-year-old with a 5-hour energy drink, especially when comparing nitrogen to the galaxy's meager oxygen reserves, a simpler atom that stars should accumulate first. The JADES collaboration continued with about 16 hours of additional JWST observations in early May. The supplementary data sharpened the spectrum, revealing 2 nitrogen states that are extremely uneven, one bright and one faint. The research team indicated that this pattern suggests GN-Z11 is filled with densely concentrated gas clouds held together by a formidable gravitational force. That's when we realized we were looking straight into the feeding disk of the black hole, Schultz said. This fortuitous alignment explains why a distant galaxy is bright enough for Hubble to see right from the start. Extremely young, voracious black holes like GN-Z11 are precisely the objects that astronomers hope will help resolve the challenging situation regarding Pfann's quasar formation. But surprisingly, even the most distant GN-Z11 is not young or small enough for researchers to accurately determine its birth mass. Schultz said we need to start detecting black hole masses at much higher redshifts than 11. I didn't think I would say this a year ago, but here we are. Until then, astronomers are employing more clever techniques to search for and study newly formed black holes, tactics like making a phone call to a friend, or in this case, another leading space telescope for assistance. In early 2022, a team led by Eös Bogdan, an astronomer at the Harvard-Smithsonian Center for Astrophysics, began regularly pointing NASA's Chandra X-ray Observatory at a cluster of galaxies they knew would be on JWST's shortlist. This cluster acts like a lens. It warps the fabric of spacetime and magnifies galaxies farther behind it. The research team wants to see if any background galaxies are emitting X-rays, a telltale sign of a hungry black hole. For an entire year, Chandra stared intensely through the cosmic lens for 2 weeks, one of its longest observing campaigns, and collected 19 X-ray photons from a galaxy named U-Zone at a redshift of 10.1. Those 19 photons, with that high-octane number, likely come from a black hole in the early stages of formation, making it the farthest X-ray source ever detected. By combining JWST and Chandra data, the team learned something peculiar and rich in information. In most modern galaxies, most of the mass is concentrated in stars, with less than 1% in the central black hole. However, in U-Zone, the mass seems to be evenly distributed between stars and black holes, not the model astronomers expected for super-Eddington accretion. The research team proposes a more plausible explanation. The central black hole of U-Zone formed when a giant cloud collapsed into a massive black hole, leaving little gas to form stars. Tremble, a member of the research team, said these observations could be consistent with a heavy seed. It's crazy to think about these giant collapsing blobs. Discovery of a black hole universe. Some specific findings from the frenzied spectroscopic competition over the past few months are likely to change as researchers peer-review them. However, the overall conclusion that the young universe has produced a plethora of massive black holes, rapidly growing and active, is likely to stand. After all, fans' quasars must come from somewhere. It said the precise and detailed numbers for each object are still uncertain, but what is very convincing is that we are finding a large population of accreting black holes. JWST has revealed them for the first time, and that's really exciting. For black hole experts, it's a discovery that has been brewing for many years. Recent studies on chaotic galaxies in the modern universe suggest that black holes active in young galaxies are being overlooked. Theoretical physicists have struggled as their digital models consistently produce universes with far more black holes than astronomers observe in the actual universe. Volin said, "I always say my theory is wrong, an observation is right, so I need to fix my theory." However, perhaps the difference indicates an issue with this theory. Maybe these tiny red dots were not taken into account, she said. Now, the fiery black holes turn out to be not just characters appearing in a universe in the making. Astronomers are wondering whether recasting objects in a more realistic theoretical role might alleviate some other headaches. After scrutinizing some of the initial images from the JWST, astronomers quickly pointed out that some galaxies appear to be so massive that it's unbelievable given their young age. However, in at least some cases, a bright black hole might lead researchers to overestimate the mass of the surrounding stars. Another theory that might need adjustments is the speed at which galaxies create stars, which tends to be excessively high in galaxy simulations. Kevi speculates that many galaxies go through a hidden monster phase that slows down star formation. They begin to be stifled in star-forming dust, and then their black holes grow strong enough to disperse stellar matter into the universe, slowing down the star formation process. He said we might be looking at that scenario. Conclusion: as astronomers unveil the curtain of the early universe, scientific intuition is increasingly giving way to specific answers. While the JWST is changing the way astronomers think about active black holes, researchers know that the cosmic patterns revealed in this year are just a prelude to what is about to unfold. Observation campaigns like JADES and SEERS have found dozens of potentially black holes from patches of the sky about one the size of a full moon. Many more tiny black holes await the attention of its space telescope and the astronomers behind it. Saxon said all of these advancements have occurred in the first 9 to 12 months. Now, we have a JWST for the next 9 or 10 years. Everything will gradually become clearer, and humanity is officially embarking on the exploration of the high-level universe. Congratulations on reaching the end of today's video. Goodbye, and see you in the next videos.